All right, I guess the doors are shut, right? So I guess that means everybody's stuck in here now. Camera rolling? Are we good on the camera? All right, excellent. Hey guys, first of all, I just want to thank everybody for being here. This is like the second to last talk in all of DerbyCon, so it's pretty great to see that there's actually some people here. I was kind of concerned when I first got my time slot that it would be basically myself and my wife, which is why I made I drug Jess here. She also helped me out on the project, so I figured she had to at least make an appearance. So today we're going to be talking about a project that I'm calling Stretching the Sandbox with Malware Feature Vectors. And I'm going to explain what those mean, but essentially it's a project that's it's kind of been on my mind for a while, and then DerbyCon kind of gave me the motivation to go out there and write some code and put some stuff out, and now I'm here talking about it. So just a little bit about me. I know about half the room knows who I am because I drug you here. The other half of the room probably never heard of me. My name is Mike Schlatt. I am actually kind of local, originally from Lexington, Kentucky, currently living in Cincinnati, where I work for a Fortune 10 company who I did not get permission to use these slides. That's why their name's not on here in any way, shape, or form, and insert a legal disclaimer there. But my day job is essentially incident response and analysis, so DFR stuff, malware analysis, reverse engineering, that kind of stuff. In a previous life, I was active duty Air Force, where I did 4 years working in the malware lab at the National Air and Space Intelligence Center. Yes. Thank you, Jason. So things that I am. This is kind of my part 2 of my disclaimer. I consider myself a hacker, specifically, IR, reverse engineering, malware, that kind of stuff. Engineer by trade or by education. I like to build things. I like to put stuff together. That's sort of what I do. I am not a professional developer, so it's kind of scary. This is actually one of the first projects that I released out there, open source. So I fully expect you guys to tear that completely up, and I'm completely welcome it. I'm also what? All right, please do it. I'm also not a mathematician in any way, shape, or form, so we're going to be talking about some feature vectors and doing some statistical analysis on those feature vectors. I had undergraduate statistics a couple times, and so I have like a very elementary grasp of what I'm even talking about. So I have no idea what I'm doing, right? But it's cool, I got this. We're going to talk about it anyways. That's why I had to bring in my wife, Jess. She's actually a mechanical engineer. She's taking all kinds of higher level classes right now, and she makes sure that airplanes don't fall out of the sky. So I had to run by anything I did before I put it up on a slide. She told me it was completely stupid, but I did it anyways. All right. I just want to go over, I guess, the roadmap for the talk I'm going to be talking about, the agenda. I'm going to introduce the project, what it is, what the motivation is behind it. I'm going to give a little bit of thoughts on sandboxing in general. I know that most people here probably are very familiar with sandboxing, which is probably why you came to this talk to begin with. But just in case, miss some people, I'm going to talk about a couple points. Feeding the beast, malware collection. So how do you actually populate your body of knowledge? I'm not going to make this like an Intel collection talk in any way, shape, or form, but there's a couple basic things that went into populating those, populating the initial Intel. Go over Cuckoo real briefly. That is basically what I used for various reasons to support the back end of the analysis here. I'm going to talk about what malware feature vectors actually are. I made them up, and what my thought process for making them up was. Then go over some of the code and some of the plots that we're able to use. And then talk about all the things that I didn't finish. So what are we talking? What are we here? So when any analyst gets a piece of malware, the first thing they ask themselves is what the hell am I looking at? I got this sample, maybe I got it from a host that was infected. If you're working in operations, you're pulling things, you're pulling collections from your guys every day. You get a sample. You might know immediately what it is because it has a particular beaconing pattern. You might know immediately what it is because of the registry keys that it creates, because of the mutexes that it creates, because of the files that it writes, the things that it drops. However, a lot of that's a very manual process. We're moving more towards, a day and age where we're getting a lot of malware in, from automated sources, and not all the time, somebody's looking, eyes on these things. And so on those cases where you're processing thousands of malware samples, or you're processing thousands of, binaries, maybe they're not even malicious, having that, assessment of what is this? How can I classify this? Can I cluster these together? Can I do that sort of grouping and correlation? It becomes kind of important, kind of interesting, especially on the scale that we work on today. Of course, there's lots of projects to do this. There's tons. I'm not even doing like a prior art page out here, mostly because I'm lazy, but also because I assume that you guys have Google. You can go out there and you can look at malware clustering. There's a ton of great things out there. A lot of it's static. One of my good friends who is not here, Coleman Kane, actually did a malware DNA project, which is exactly the same type of goals, but using static analysis. So the second part of the objectives here, or the motivation, is we got a ton of data from our sandboxes, right? I mean, we run everything through our sandboxes. I don't know about you and your organizations and how you guys operate, but we get a sample. The first thing we do is we throw it in a sandbox. And we do this sometimes for our virus total hunting. We'll be pulling down hundreds or thousands of samples, and we throw them through an analysis engine. And a lot of times that data just kind of sits there. Nobody ever looks at it again, right? I mean, these things generate hundreds of megabytes worth of data, and it just kind of sits there. We have it, so let's put it to use. I've worked on a couple different projects to correlate some of this stuff together. One of them at work has been my baby for the past year. I'm not presenting on that today, but this one is something that I think that we can share and look at. Would like to have some other eyes on. So here's where I talk a little bit about sandboxing. Again, I'm not going to beat this down too hard, because I figure that most people are pretty familiar with what sandboxing is and the concepts behind it and why you do it. Traditionally, you have your static and your dynamic analysis tools that people have been using for years. And the whole idea behind sandboxing is that we want to automate. We want to create an isolated environment for automating system observation. And sandboxing's really exploded over the past 5 years. I remember prior to 5 years ago, there really weren't a whole lot of first of all, there wasn't a whole lot of open source anything. I think the Cuckoo project started about that time, but there were maybe one or two vendors, and they were charging a whole bunch for their sandboxes, and then a lot of people were kind of rolling their own at that time. But over the past 5 years, it's kind of taken off. So just a couple thoughts on rolling your own versus vendors versus open source. I don't want to start like any sort of like war here by talking about this, but just my 2 cents on kind of the pros and cons. If you roll your own sandbox, you have your control over everything. You can do very custom. You can do very custom anti sandbox, I guess. I don't know if that's like a word. Anti sandboxing techniques, so you can really have full control over what that looks like. And a lot of times, if you roll your own, the guys that write the malware, they aren't going to have the inside baseball knowledge of what you're doing to try to evade that. Same kind of thing with a vendor, except for you don't have any control over it. The vendor has all the control over it. They also charge a lot of money, so there is that to consider. And then there's open source, and there's there's major advantage, major disadvantage. Major advantage is you got this great community that supports it. It's constantly being updated. The features that something like Cuckoo's offered over the past couple of years has just absolutely exploded. Major disadvantages is that, yes, a lot of malware does evade it. And I just want to throw that out there because I know somebody in the audience is like, I don't use Cuckoo, malware evades it. Absolutely, that's absolutely true. So you got to know what you're dealing with, and you got to know, it's definitely possible that malware is evading your open source sandbox, and you need to, kind of take that with a grain of salt. So basically the way that we operate in our environment is we throw everything through Cuckoo. And we get back reports. We can kind of tell, hey, this thing exited immediately, didn't really do a whole lot. But even the way that it exits sometimes can be very useful, especially when we get into this project. It's still going to generate feature vectors, which obviously we're going to talk about, that are kind of unique, depending on its anti-VM, anti-sandboxing techniques. Those can be fingerprinted as well. And if you didn't know, we're using Cuckoo for this project. All right, so feeding the beast. Again, I don't want to belabor this point, but so the whole idea behind this project is we're going to take unknown samples and we're going to try to classify them. Well, you have to start with something, right? You have to start with your known knowns. So to start with the known knowns, you have to have some sort of malware collection. You have to have some sort of Intel program or some sort of process. It doesn't have to be elaborate. Maybe it's elaborate. That's going to depend on your organization. I'm not going to tell you how to run your organization's malware collection or Intel program. I'm just going to say that for the purposes of this project, there's a couple pieces of information that I collected. I collected hashes. I collected the source that I got the samples from. I collected the source that's supposed to say date, not data. I collected the file type and malware family. So for the purpose of this project, I basically went out to, open source research where, somebody like SecureWorks or, FireEye or somebody released a report on some malware attacks and said, hey, these samples belong to the same, malware family. And I said, hey, this report on this report date said these hashes belong to this. This is the file types they were, because when you actually do an analysis, file type's very, very important, because apparently a DLL acts very, very differently than an exe as far as when you actually execute it in the sandbox. And of course, how do I do this? I create an awesome spreadsheet as I'm just going through these reports, dump it straight into a CSV, and I actually created a tool that is part of the project, kind of tangentially, addtags.py, and it will basically take all that great data that you've dumped into a CSV and put it into a very simple table. This table is super, super simple, and the purpose behind it is just to put all that information in a relational format so that you can easily tag it and associate it with your analysis. So Cuckoo Sandbox reports. Most people, when they see Cuckoo, they look at this. They get the pretty web interface, and that pretty much shows them what they need. I think most analysts that I know don't really go further than this. They look at the report, they see the things they need to see, they make it a determination whether or not they think it's malicious. They might copy some of the C2 down into some sort of repository. We use crits, if you guys are familiar with that project, and then move on with life. Well, there is a lot behind the scene. There are these awesome, like 500 megabytes or up to 500 megabytes JSON reports. It's just nothing but raw data, and that's really what we're going to be looking at. All right. So, malware feature vectors. What are we talking about? So, when I started using the word feature vector, I wasn't even exactly sure I was using the right word, but the definition from Wikipedia makes me think that maybe I am. I don't know. So Wikipedia says that a feature vector is an n-dimensional vector of numerical features that represent some object. In the example that they actually used, they said, well, usually you're going to see this in like image processing and signal processing and that kind of stuff, but you can also think about it conceptually like, well, if you want to create a feature vector of all the fruit that's on a table, you can say that you have 4 apples, you have 9 bananas, and you have 10 pears. And then your vector at that point would be 4, 9, 10. And that's just a very easy way to just assign some numbers to a feature set. So when we're talking about malware, what I've decided is that what if we try to assign numerical values to the artifacts that we see in this, dynamic reports. So things like number of API calls, registry keys, mutexes, network connections, DNS callouts. All those you can kind of count them up and add them onto a vector, basically. Now, of course, you run into some issues that we're going to have to deal with, like, well, maybe you're going to count the number of strings, and that's kind of important for a particular malware family. They usually have, 10,000 strings or something, but they only make 2 DNS queries. Well, maybe those 2 DNS queries are just as important. Well, obviously, you're going to need to do some sort of normalization in that case. You can also do things like, the bytes of a buffer copied or bytes of network generated. And then last bullet there, it says, normalization and uniformity in comparison. So created a script, basically, that is titled createFeatureVector.py. In case, it wasn't painfully obvious from the title what it does. It basically turns JSON reports from Cuckoo into these feature vectors that we can then store in a database. So the process is pretty simple. I'm not going to go through all of this, but essentially what it does, and this is kind of a first pass, like I just want to get some numbers down to see, what I'm dealing with here. it goes through each of the major sections of the Cuckoo report. So you can see down there at the bottom, networking items. It says, if network is in the JSON report, count all the things and add it to a feature called network, underscore the key that's in that network iter items. And so what that does is it allows a little bit of flexibility because not all reports contain all the things. So you are going to get a little bit different, results every time you run these on a feature set. Same thing for static items, drop files, the behavior summary. So I actually created this from the newest version of Cuckoo, the actual dev version, where they actually changed up the report format quite substantially. So this actually, at this point, does not work for 1.2. It only works for the 2.0 dev. If anybody wanted to go out and make this backwards compatible, they could. I probably will because we're going to have to for our operational environment. So that is forthcoming. But essentially, this is just very, very simple. It just goes and it counts all the different types of data that Cuckoo's recording, calls that a feature, and then puts it in a dictionary so that they're always associated with each other. Because if you just put them in a straight array, they won't line up and stuff. So then some behind-the-scenes stuff that happens is once you've collected a substantially large number of these. In fact, I kind of front-loaded all the samples. I think I front-loaded about 300 samples, different actual MD5s and 40 different families into the set. You're going to want to do that whole normalization process. And so the way that normalization process works is essentially you're going to want to calculate the max values for all of the features that you collect, and you're going to want to calculate the min values, or you can just cheat and assume that the minimum value is 0. Then you're going to obviously want to divide for each vector, you're going to want to divide by the max value. And so you're going to get a number that's between 0 and 1 for each. And that can only be done after you have a substantially large number of features calculated, because who knows what your max value is going to be if you only have like 2. And I wrote functions in this project that will, anytime you want to like recalculate, renormalize, you run it, it'll run for a few minutes, and it'll renormalize all your vectors. When the vectors are actually stored in the table, they're stored in a raw format. They're not stored normalized for that exact reason. And but it does store the max values so that you can quickly use those and quickly reference those as you're calculating the normalized vectors. And the vectors tables kind of just looks like this. You just associate the hash. The machine is very important. So one thing I did not mention when I talk about the Sandbox setup, the biggest thing in dynamic analysis is uniformity. So you don't really want to be comparing a 32-bit Windows XP machine to a 64-bit Windows 7 machine. It's very important that those are treated as separate groupings. Task ID, so you can tie it back to the Cuckoo report. Just the type of vector or type of vector it is and the value. So vector type would be like network connection. Value would be like 8. All right, so the rest of this presentation, I'm going to kind of go over what we've presented and some of the results, and kind of walk through the project a little bit. So the main part of the project is mfv.py. It's kind of the core resource of the project. It defines, what the vector class is. It lets you interact with the, database, so you don't have to do any, raw SQL queries or anything like that, unless you want to, of course. And it defines, your basic functions that are going to manipulate the vectors, perform some statistical analysis, and display plots. So I created an examples directory within the project that basically has, right now, 4 different scripts that perform, that give you some plots. And we're going to go through those to kind of walk through what we're talking about. So autogenFamilies.py. The whole purpose behind this script is to group the vectors based on those tags, family, file type, source, and then normalize them and then create something called an archetype. So the first part of this is very important. It's where you take those samples, those tags that we already inputted into the tags table, and then you kind of break those up into unique, what I call labels. And essentially what those are is, the family that you've said that it belongs to, the file type it is, the source that you got to. It actually has the source date as well, but I didn't put it up there. And it pulls those out. It takes all the features that are associated with each of those, and then it normalizes them as part of that group. And the second thing it does is it creates an archetype. And essentially what an archetype is very key to this entire project. So what is an archetype? what I found is that, directly comparing all features for every vector showed a very low correlation. This wasn't getting very good results, honestly, because you're talking about, you have a lot of different vectors that do very, very different things. So, and to think about this conceptually, it's pretty easy. If you think about, particular malware samples, you know that they have kind of their own calling cards, right? So a particular sample might create mutexes of a particular nature, and that's very important, to define that sample. Another sample might create a whole bunch of domains as part of the domain generating algorithm that it uses, and that's a very important facet of that malware family. And so comparing those things directly to each other don't really make a whole lot of sense, because one sample might not even create domain names, and another sample might. So the solution to this was to actually compare only the things that matter for a sample, for a family. So I created a function that tries to figure out what is most statistically significant for a particular group or family. It tries to figure out which of those tags, which of those features really makes the biggest difference. And so the way that the archetypes are created is essentially you give it your subset that you're interested in, which is basically all the samples that match a particular label that we just talked about. And then you also give it the superset, which is all the samples in your universe, I guess. And then what you do is you say which features have the lowest amount of variance in the lowest amount of variance once it's normalized in the subset, but the greatest amount of variance in the superset. So it's as simple as taking the variance of each of the vectors and then subtracting them and then figuring out essentially what are your top 30 samples, or sorry, what are your top 30 features that really define that sample. And so just kind of walking through that code a little bit. First thing we do is we're going to prune the vector, because if you care about, you really don't care about a lot of zero values for the most part. I mean, there might be some weird cases where the fact that there are zero, network connections or something really defines a sample. But for the most part, you don't care about the zeros. There's a lot of zeros. About 255 features total from the 300 samples that I looked at, and I think most samples only actually had about 100 non-zero values. So first thing you do is for the subset, get rid of all the zeros. Then you're going to want to find the standard deviations for both sets, like I just talked about, and you're going to want to do that on a per feature basis. And then you're going to want to find the difference between the subset and the superset standard deviations. And then you want to take basically the top 30 or the lowest 30. It's going to be a large negative number is what you're going to want. So all that, and skip down to the bottom, basically it's going to return a very pruned set of features. So instead of having 255 features where a lot of them are like zero, you're going to get like 30 features, and they're all going to be statistically significant for the subset that you provided as compared to the superset. So then the idea behind using archetype is then you can compare unknown samples to that archetype to see, hey, does this fit the curve? Does this fit, how close are these vectors? What is the Euclidean distance, between these vectors at this point? But you're going to want to actually calculate the same feature sets from that archetype for each archetype that you want to compare a sample to. Does that make sense? I kind of stumbled on my words there. Cool. So, and then once you calculate these archetypes, you want to be able to quickly retrieve them. You don't want to have to do this every single time. So it stores them in the table, and just like the max values that you use to normalize, there's functions in there that you can re-archetype, redo. Also, it's nice because you can actually go in here and manually edit some of the features, and once I start showing some plots, it'll make sense when you're going to want to do that. So then the output of AutoGen families is it kind of just gives you some stats on each of the labels. So the labels look like something like this. So you got plugx, PE32, EXE. Got it from SecureWorks on 2015-08-05, and it ran it through Windows 7 x64. And so that's kind of like the unique identifier for this family. And then it tells you some stats about that family that it created. It tells you, each sample is the mean Euclidean distance is 0.26. The units on that don't matter because it's completely normalized, so it's 0.26 somethings. Standard deviation is 0.07, and then it kind of compares that to the rest of the samples in your universe there. So you're talking about having, a mean distance of all samples is as 0.6. That's roughly 3 times longer, but the standard deviation is much higher. And then so the next thing it does is kind of give you a little bit of a sanity check. It tells you that there are 48 vectors that belong to that family that can basically be defined by that label. And the number of all vectors within one standard deviation is 40. The number of all vectors between one standard deviation, or 2 standard deviations, is 51, and within 3 standard deviations is 113. So what you can see there is somewhere between 1 and 2 standard deviations away, you actually get all of those vectors. And you can drill down to make sure that those are actually catching the ones that you think that they're catching, and they are for the most part. There's a couple outliers, and we'll go into that. Last thing it does is it actually plots the entire family in Plotly. I don't know if you guys ever used Plotly before, but it is interesting. I basically chose this for this project because I wanted to use it. I know that it's probably not going to work for a lot of large organizations that have restrictions on like putting their data in the cloud, but essentially I've heard Plotly described as GitHub for plots. So it's pretty cool. It allows you to, it's very interactive, but essentially all your data belongs to them. So it's totally not something that is going to be feasible for a lot of corporations, but you can easily adjust this. And so this is like what one of the family plots is going to look like here. So you got all your samples over on the key, and then on the x-axis there you have those features that were defined as being statistically significant on the bottom. You guys are fine. It's cool. All right, where were we? So you can see that I drew both the mean line there, which is basically the archetype, and each of those archetypes. I know you can't probably read except for the guys in the front row there, but it has the different the values that make that archetype up there on the x-axis, and you can see where each sample goes. So you can see over on the far, left-hand side of the graph there that there are some samples for API stats NT duplicate object that are significantly above even 1 standard deviation. So what that tells me is that's something that I might want to manually tweak this feature vector for. Maybe I don't want that guy in there because it's just too far out of the average. I don't know. Something that we can tweak around with. We can play around with. Here's another example with even more. This is a Carbonac family group here that I got from We Live Security blog post. A bunch of hashes were able to pull down. And you can see that they're all pretty tightly grouped. But I really like to see those outliers. I really like to see that there are 2 random samples, and if you go and you kind of follow them through, and in fact, even if I zoom in, at the bottom there, you can see that there's I think it's a sample 490 that's kind of just kind of outlying. So what does that mean? That means there's a really good chance there's something up with that dude. That dude's doing something really different. Obviously, the graph's not going to tell you what, but it's going to tell you that of the 100 samples that I dumped down, maybe that one is doing something that you can go look at. And a real quick comment here on the shape of these plots. So I ordered these, again, the actual numbers themselves aren't really all that important, and the order themselves aren't that important. These are really more, these could be more like bar graphs, but bar graphs are really, really difficult to put like 100 of them on the screen at a time, so that's why they're more like a plot. And I order them from least to greatest. So those on the far left there are actually really important, and they're just as important as the ones on the far right, even though they are physically smaller. Cool thing about Plotly is you can zoom in and you can see them, but that's just kind of a comment on the shape of the graphs. Here's another one where the malware family is pretty tightly grouped together. So this is an example of a excuse me. This is an example of a family group that I think is pretty solid here. Some ghost samples that I recently pulled down and ran through the system. So second example script that we have, plot archetypes.py. So this is actually very similar to the previous one, but it just gives you less noise, essentially. So it uses the database instead of creating the archetypes. So the first one takes a couple minutes to run. With the sample size that I think I had about 1,300 analyses. I had 300 samples and about 1,300 analyses. It takes maybe, I don't know, 4 minutes to run that first script. This script will run pretty much instantly. because it pulls the archetype straight out of the database and it just plots them, and only plots the mean and standard deviation. So this just really gives you a good feel of the overall distribution of how tight your standard deviations are and stuff. I'm not going to go through this, but there's code. There's code that makes it happen. So this is kind of just what this gives you. It just gives you a good overall feel. You can see that this one's pretty tight. You can see that there's a couple features here. The behavior API stats, find resource. So the find resource API call is kind of all over the place, something that maybe you would want to manually remove. So this is, again, it's another good visual way of saying, hey, these features are really tight. They're really, the standard deviations are really close to the mean. We really want to use those. And the ones that aren't, you can say, hey, what if we just manually remove those next time that we define this function? Here's an example of one that's not very tight, and I might want to do some more work on this. And again, these plots are only going to be good as the data that you put into them, right? So what I found is that a lot of the automated threat streams, sometimes they don't tell the truth when they just give you a hash dumping, right? They just give you a whole bunch of hashes. They give you 200 hashes, and they say, hey, all of these belong to PlugX, or all of these belong to Ghost, or all these belong to DryDex or something. And turns out that they not 100% there. And so if you're just dumping in stuff from particular threat feeds, you might find that they have a much wider variance in their feature set standard deviations, and that's a very good way of kind of vetting your intel sources. Is that man? Possibly. I mean, I like I said, I was only dealing with 300 samples, so I didn't really get too far into that. Mm-hmm. Yep, absolutely. Yeah, so that's why I always include the date of the report that I got it from. Again, like I said, I got these pretty much all from open source reporting. Was pretty much my only source for hashes and whatnot, and I always made sure that the date was something very, very important to distinguish it as separate. But absolutely, yeah, I mean. You're going to get completely different results from CryptoWall from this year than you got from CryptoWall 2 years ago. CryptoLocker, I guess. All right, so bestguess.py. So this is the script that kind of does the, hey, I have an unknown sample. I want to figure out which archetype does it most closely fit to. Obviously, if it doesn't fit to any of them, it's still going to give you an answer, but it's going to give you an answer that's wrong. That's the way that works, right? So it compares the test vector to each of the stored archetypes. It normalizes and prunes the sample to fit that archetype. I think I kind of explained that process earlier, but the whole idea is that you take the sample, you take the analysis that you get from the Sandbox, and you only look at the features that are relevant to that archetype when you're doing your comparisons. Then it finds the Euclidean distance from, from test vector to the archetype and then it also finds the Euclidean distance between the archetype's vectors to the archetype's mean to find the standard deviation. It figures out how many standard deviations away your sample is based on the average standard deviation that the internal family's vectors were from the internal mean. If that didn't make any sense, we'll have to talk later. It's kind of hard to explain, but essentially what you get is you get how many standard deviations is your feature set away from the archetype's feature set, and based on that, it can rack and stack them and say how close they are. When I ran this through my sample sets that I was running, again, it's a relatively low number of samples, about 300. It showed that the number one guess was 75% correct. Basically, it had no knowledge of who it was or what it was, and then after the fact, I was able to go back and say, yeah, yep, you told me correctly 75% of the time. The first top three, that number jumped to 98%. So when you take something completely, I think we can absolutely get better numbers in this, and I think the way that you get better numbers in this process is you prune the feature sets even more. You go back, you look at those graphs, you say, hey, this has too much standard deviation, so let's remove that one. Or hey, I happen to know that there's one in here that needs to be that's not, and then you kind of shape those a little better. Another way is you populate it with more data. You give it more samples. You give it more you give it more, intel to upfront. And you make sure that the samples that you actually say, once you say a sample is, a particular thing, it really is. But, top 3, 98%, I think is pretty good. And so here's kind of the output of what that looks like. It's going to tell you, first thing it's going to do is going to tell you the distance from your vector to the archetype, how many standard deviations, then it's going to rack and stack them and pretty much tell you your best guess. So there at the bottom it says, best guess for this guy is Carbonac P, whatever, 32, let's see. So what happens if so how can you verify? How can you verify? What if you truly don't know? Obviously I cheated because I used samples from itself, so I knew what they were ahead of time. Well, the system didn't know, but I knew. So what do you do if you truly don't know? Well, you can look at it graphically. So compared to archetypes.py is the final example here, and essentially what it does is it normalizes and prunes the sample in the same regard as the previous script, but then it plots it against all the archetypes. And what it does is a very visually easy way that you can say, hey, this really fits that curve, or it doesn't fit the curve at all. And it's a graphical way to verify best guess. So here we go. Here's a quiz. So what these samples are right here, what these plots are right here, is you have the sample under test is in red. The blue is the archetype that's being compared to, and then the yellow and the green are the standard deviations away from the blue. So if I'm just looking at my plotly graphs, which one does the red most follow the blue? Yep. Pretty easy, right? I mean, you can see this just scanning across those. You can see that's one that fits pretty much almost exactly. And so when you actually open that guy up, I mean, you can see it follow the curve right there in between the two, the upper and the lower limits. So, and here's an example of where it was wrong. So best guess told me that this should have been the #1 guy. So it's not, and it's very clear that it's not. You can see red dots that are clearly outside of the standard deviations all across the board. So the second guess was actually this dude. And so if you had to choose between the first guess and the second guess is right on. So again, it's a pretty nice way to graphically verify, if your best guess was correct, or if your best guess gives you 5. Basically, I've determined if you go and look at the graphs, you can pretty much tell that the first guess was completely wrong for whatever reason, but the second guess was right. So that's pretty much what I have right now. I didn't quite get as far along in the project as I want. I mean, nobody ever does, right? So what are the next steps that I currently have for this guy? I want to operationalize this. There's a couple things that I didn't do that I would like. For one, I would like to create a cuckoo reporting module, so this is automatically generated every time you run it, and that's literally next on the list. I didn't actually get that finished. I have standalone Python scripts that will basically interact with the API right now. So if you have a Cuckoo server that's running the API, you run the script, it'll pull your stuff, it'll ingest it into these databases so that you can run the rest of the scripts. But it would be really, really nice if it was just kind of built into Cuckoo from the get-go. And additional features, right now it was very, very simple stuff, right? So all we did was count. All we did was count the number of essentially tags that Cuckoo created for these samples. I would like to do some more sophisticated stuff, like look at the number of bytes that are passed through buffers, look at the number of bytes that are passed through PCAPs, look at some of the more things that are more intrinsic than just counting. I'd like to create some sort of front end so that you could easily edit your archetypes without having to be a SQL person and go in and manually edit them in SQL. And cluster graphs. So the one thing that you didn't see is you didn't see any cluster graphs. You didn't see where you could take a whole group of samples and then put them on a single plot and see how close they were relationally. The challenge there is that when you have an n-dimensional vector and you want to plot them on a two-dimensional space, you're going to lose data. And there's all kinds of theories out there, what the best way to do that is. But at some point, you're gonna lose data. And the way you lose data is kind of important. So I'm in the process of trying to vet out a couple different solutions to put these on, all these on a cluster graph correctly. If anybody has any suggestions, I'd love to hear. thoughts on that. But that's about it. So questions, guys? Yeah, it makes no sense, right? I'm gonna have to talk to you later, dude. I don't know. I'm not a mathematician. You're gonna have to explain these things to me. No, seriously though, it's probably a much more intelligent way to do that. I'd love to work at that. Hey guys, thanks for watching the presentation. Come hit me up. Tell me how stupid I am for not using bounded distributions, and let me know what you think of the project. There's the GitHub address. But thanks, guys.